So if you spend 5 minutes on this question, then you're going to miss some other questions just because you didn't get to them. So even if you get a question correct, it's really important to go back and see how long did I spend on it. And if you spent a long time, see if maybe there's a faster way. See if there's a shortcut.
Phil back for some more MCAT podcast, continuing our breakdown of Blueprint MCAT full-length 1, which again you get for free when you sign up for the diagnostic exam from Blueprint MCAT. So go sign up for that if you haven't already, and then you can follow along with us.
Yeah, the free practice test bundle comes with diagnostic, this exam that we're working through, as well as a bunch of other stuff. You have access to some QBank stuff, some like content review videos, just like a bunch of little things to help you kind of like work along. And it's free, so literally everyone should get it because it doesn't cost anything and it'll help out with the MCAT prep.
Free. It costs an email address.
Right.
Which everyone gives out for free these days. All right. So again, kind of going through the mindset of this as well. As we switch from passage 3, we get to discrete set 1. Is that always going to be the kind of flow? Assuming, right, we're back into the normal MCAT time frame of 7.5 hours, full test. Assuming the AAMC actually goes back to a full test after going, oh, wait, we can give a 5-hour test and we can fit double the students in. But anyway, assuming regular test, is it going to be 3 passages, set of discretes, or will that fluctuate?
I want to be very careful about saying always because they may change something and someone's going to be very mad at me. But generally, this is what I've seen on all the exams I've ever seen. So I think it's fairly safe to say generally, this is the way you're going to likely see this. Okay.
So hopefully a little bit of a break for a student who's tired of reading passages. They get to the first set of discretes. What's the first thing that they should think about before they jump into these discrete sections?
Well, I mean, in theory, I actually, like in review, I like to look at, if I'm trying to figure out like how to help a student and I'm working with them, I like to look at how they do on the discretes versus the passages. Because if they're missing a lot of discrete questions, very often they're struggling a little bit with content and there's just like something they just didn't know or some problem there. They miss a lot more passages. That could be like a data interpretation kind of thing. Or like maybe this passage was about magnetism and they're just like not very good about that specific content thing. The discrete sets tend to be just kind of a random grab bag of a bunch of just kind of like different things. And so there's not really much you can do to prepare other than just jump into them one by one. In theory, they should be quicker than the other ones because you don't have to read the passage. You don't have to refer back to anything. Everything in general is contained in the question.
Okay. All right. Question 14, I'll read. What are the formal charges on the atoms in the molecule below? Note, the molecule has not been labeled with overall formal charge and may have an overall formal charge that is 0 or a value other than 0. Thank you for that note. All right, and so just kind of describe this if you're listening to this. We have Roman numerals 1, 2, and 3. Underneath Roman numeral 1, we have an oxygen with 2 little dots on the left, and I'll let you describe what those are, but I'm just going to tell you what I see. I see what looks like a triple bond to a nitrogen underneath Roman numeral 2, and then underneath Roman numeral 3, connected to the nitrogen, is another oxygen with 6 dots around it. So that's what I see. So what is the for the student who actually knows what this is and how to actually describe this, what is the actual terminology potentially for what I'm looking at?
I think it was pretty spot on with the bonds. You have a triple bond and a single bond there with the 3 lines versus the 1 line. Other than that, I just call it a lone pair. Okay. So the oxygen on the left has a lone pair and triple bonded to a nitrogen, which is then single bonded to another oxygen with 3 lone pairs.
3 lone pairs. Okay. All right. So then we have answer choice A. Roman numeral 1 is +1 charge. Roman numeral 2 +1 charge. Roman numeral 3 a -1 charge or -1 charge. Answer choice B, -1 +1 +1. Answer choice C, +1 0 -1. Answer choice D, +1 -1 -1. Now, I think it would be fun if the MCAT actually made it really hard and mixed up the order. So, like, answer choice A would be Roman numeral 1, 2, and 3. Answer choice B would be Roman numeral 2, 1, and 3. And then you have to, like, rearrange it in
Just
your head.
like, yeah, bounce it all around.
That would be mean. Okay. So really, again, going to what is this asking? It's asking what are the formal charges on each of these atoms? And it tells us that we don't know what the overall charge is. It doesn't tell us what it is. So it could be 0. So it's kind of a nice little hint to say it doesn't have to add up to 0. It could be something other than 0.
That's actually good to note because NO2 is generally nitrite, but this is not the nitrite most people are familiar with. So if you know the charge, like you got to throw that out. And then the question here is telling you like you can't predict the charge. It's going to be something weird.
Yeah.
So go from there.
Yeah, and so we just have to kind of use our chemistry knowledge here and go, okay, what do these bonds do to the charges and what do the lone pairs do and all of that fun stuff. And I don't remember any of that. So discretes for me, right? Going from what we said, I think last week, where it's like, I use a lot of logic potentially to get these passage-based questions right. The discretes throw me off because it's really based on knowledge, which I don't remember anymore.
Right, which is exactly what I was saying at the beginning. Like with students, I'll look at their like exams, the passages versus the discretes. If they're missing a lot of discretes, it means they're probably missing some content. Versus if they're missing passages, maybe it's a thought process or a reasoning side of things we need to kind of work on.
It's an interesting question, knowing that the Blueprint MCAT course has really awesome analytics. Is that part of the analytics kind of algorithm to say, well, you're missing a lot of discretes compared to the passage-based stuff? Maybe there's some content gaps there.
It does keep track of that, the discrete versus passage stuff.
Cool.
The analytic stuff, super exciting. Really having a good time looking at all of that. The more data thing that the scientist inside me is always screaming for. He's happy for now.
Okay. All right.
So going into this, we have to figure out how to calculate a formal charge. So I'm going to give you the equation for formal charge, which is the number of electrons normally found on the element or the atom, minus the number of sticks and dots. The idea here is the dots are lone pairs of electrons. A bond is 2 electrons, but they're being shared sort of unevenly. Or evenly in this case. And so we have the oxygen has 2 lone pairs, and it's kind of got 3 electrons that from those like double bonds. Each of those bonds is 2 electrons, but one of them kind of goes with the nitrogen, one of them kind of goes with the oxygen. Hopefully that makes sense.
No, but yeah.
Yeah.
And so I pulled up the periodic table here. Does the periodic table help me understand how many electrons are normally there?
Right, yes. And so anything on the far right is going to have an octet, so with the exception of helium. So like neon, argon, krypton, xenon, all of those are going to be like 8 valence electrons. Then you go to the left, they're missing 1. So fluorine is going to have 7 valence electrons, and oxygen is going to have 6.
Yeah.
Right.
And that's what I kind of remembered. I'm like, okay, I counted. I said 1, 2, 3, 4, 5, 6. I'm like, okay, so oxygen should have 6. So using the equation that you just said, I should start with 6, and then I subtract the number of dots and sticks.
Yeah, so, just kind of add them together. So a bond counts as just 1 electron, and then any free electron counts as an electron as well.
So if I look at this properly, I see 6 minus 1, 2, 3, 4, 5 for this Roman numeral 1. So 6 minus 1 is plus 1.
Yep.
Okay. So plus 1 gives me answer choices A, C, and D. So B is immediately out. So I'm going to strike that through. All right. And so nitrogen should have 5 minus 1, 2, 3, 4. 4 sticks connecting to this one. And so 5 minus 4, again, I'm left with plus 1, which leaves me answer choice A without looking at answer choice 3. And I'm going to work through it just for fun anyway. So again, oxygen, 6th column here, so 6 electrons, minus 1, 2, 3, 4, 5, 6, 7, minus 1.
Yep. Very good.
Okay.
And once you know that equation and you're good at kind of applying it, this question's actually pretty straightforward, but the challenge is like just making sure that you've got that little outside discrete knowledge.
Okay. All righty.
So on to the next one, where we go into a little bit of projectile physics-y kind of stuff. My kind of question. So a mass of 10 kilograms is dropped from a height of 20 meters. Ignoring air resistance, what is the maximum speed achieved by the mass? Assume g is 10 meters per second squared.
Yeah, I forget this equation. And so 20 meters, 10 kilograms. We know gravity here is saying, hey, 10 meters per second. What is the maximum speed? Yeah, I don't remember the equation, but let me see if I can just use some logic here and go, okay, what is this? We have 20 meters, and if gravity is 20 meters per second, I don't know if that matters. And we have a mass of 10 kilograms. 20 meters. I don't know. Yeah, so maximum speed, not acceleration, speed.
For a velocity overall.
Velocity. Now, does the velocity change based on weight? So I don't know. I think it does, right? Because we have a feather. The speed that goes down is not very fast versus a bag of bricks. So the speed does change. So let me get that out of my head, because I think it might be easy to go, oh, the speed shouldn't change, right? And they choose A, gravity. It's going to go down by gravity. So A is, I'm going to throw out right off the bat. And then D just sounds way too fast, right? It's like 400 meters per second. That's very fast. So I'm gonna go with C, just because it's faster than 20 meters a second and it's not super, super fast. So I'm just going to go with C without remembering the equation.
I like your kind of like just ballpark, like you very clearly, like, I'm not really sure what to do with this, but D is very fast. Like putting D's speed in like conceptual, like understanding this means that every 5 seconds, this thing's going to go 2 kilometers. That's very fast. Like this is a very, very fast thing. Yeah. Answer choice C is also
very similar.
Really
yeah,
fast.
It's very fast too. When you say
like
it that way,
means every 5 seconds it's going a kilometer. Like that's a really fast. What is this? Like a mass. Whatever this thing is. It's like this thing's like 10 kilograms. Like if you drop it from 20 meters, it's not going to be going that fast. That's like crazy. Just kind of like a little bit. Just doesn't make sense.
Yep.
Which kind of helps us get down to A and B.
Yep.
Now there are actually 2 ways to solve this question. The way that the MCAT kind of sets this up, you can use your kinematic equations. You have your like initial velocity is going to be 0. We're trying to find our final velocity. We have the distance is 20 meters. Our acceleration is going to be 10 meters per second squared. So you can use your kinematic equations for that. I actually don't think that's the easiest or best way to solve this. If the MCAT ever asks you for velocity, there's kind of 2 things that should run through your head. One is kinematics. The other one is energy, kinetic energy. Very interestingly, there are some cases where kinematic equations don't work, where the forces are changing. Like as objects get closer, they pull more with like electrostatics or gravity or things like that. Or springs, the more you compress it, the more they push back. And so in those cases, you kind of can't use kinematics, but you can still use energy. So as a result, because for a lot of questions, you can use one or the other, but some questions you have to use energy. My gut for telling students is like try energy first always, because in theory that should work unless there's some weird like frictiony, draggy thing kind of going on to be clear about in the question, because normally we assume that isn't the case. And so in this now, we just have to convert our gravitational potential energy into kinetic energy. And so the potential energy equation is mgh. Kinetic energy is 1/2 mv squared. So interestingly, mass is on both sides. That cancels out. So GH equals 1/2 v squared. And so this actually runs a little counter to what you were saying a moment ago. So technically, if we ignore drag, a feather and a bag of bricks, they're going to fall at the same speed.
I've seen those experiments on YouTube with the vacuums.
Right. In a vacuum, if you like pull out, and like it's really cool kind of like seeing that happen.
Yeah.
The problem is the drag. And so we're assuming there's not going to be any drag in this case, especially because we're only dropping it from 20 meters. If we're dropping it from like the Empire State Building, like it's going to reach terminal velocity, but probably not in this case. So the mass ends up kind of canceling out. So we end up not needing to worry about that. So we just have GH equals 1/2 V squared. You can multiply by 2. So you have 2 GH equals V squared. And then you can just plug in the numbers to find the velocity. So G is 10, H is 20. So we have 2 times 10 times 20, which is 400. Square root it, turns into 20.
Okay.
I feel like that might be easier to follow with a whiteboard app.
Yes.
But yeah. So takeaway there. Try to use kinetic energy.
Okay.
Right. Like if you are a student, prepping for the MCAT, you ever see a question where they ask for velocity, kinetic energy should be your go-to first. See if you can convert like gravitational potential energy or electrostatic potential energy or spring potential energy into velocity through kinetic energy. Not only does that almost always work compared to the kinematics, it also, I think, is easier in terms of the math that because the kinematic equations can be kind of complex at times.
Okay. Question 16. How many tetrahedral stereocenters are present in cholesterol? Pictured below. All right, so if you're listening to this, it's just a standard kind of drawing of cholesterol here. And so it's asking for tetrahedral stereocenters. So again, very strict kind of definition. Do you know what a tetrahedral stereocenter is? We have answer choice A, 2, answer choice B, 6, answer choice C, 8, or D, 9. So I have no remembrance of what a tetrahedral stereocenter is. If I try to break down the actual language, what's tetra? Is that 4 or 6? I forget.
It's 4.
4, yeah. So tetra is 4. So 4 stereocenter. So something that has 4 connections to something else. Yeah. And so stereocenter, to me, the definition of stereocenter means like, is it the same on all sides because it's a stereocenter? Is that what that means?
So with the stereo, you have like right and left.
Mm-hmm.
Like if you like listen to something in stereo, that's different than just like the one speaker. So stereo center means you have a right and left version of the center, which is another way to say a chiral center, right? And so tetrahedral, a chiral center is something that's like got like connected to 4 things. It's tetrahedral, and it's also got some stereochemistry with the like right and left hand version of this as well.
Interesting. So potentially connected to 4 things. And so if we just look at this, like, okay, 1, 2, 3, 4, maybe that's 1 there. 1, 2. Do they all have to be different?
Yeah, because otherwise they won't be stereo centers. So stereo center means there's got to be a difference from one side versus the other.
Interesting. So if I look at, as I'm kind of using my mouse here, I'm looking at kind of the middle here, and I have this carbon that's attached to the hydrogen here, just straight up. The little wedge going straight up. To the right, it's going to another carbon that's attached to hydrogen and another carbon over there, and that's good. They look very similar. I don't know. Yeah. This is hard.
So this is one of those questions that students very often end up taking like 3 or 4 minutes, which you definitely don't want to put in that much time.
At a glance, I'm only seeing 2 potential places here that look like they would be tetrahedral stereocenters if I were to think through that.
So I actually hinted about this, I think last week it was the week before with the
the dashes and the wedges kind of shortcut here.
Yeah, because the only time you would include a dash or a wedge is if it matters, which means there's a right and left form.
Oh, so 1, 2, 3, 4, 5. Well, there's 7. But that's a wedge there too. Darn it. 1, 2, 3, 4, 5, 6, 7, I see 8 dashes and wedges.
And that's it.
Darn it. I wasted all that time going, wait a minute, what about this one?
Like one atom at a time. Okay, there's an alcohol, there's a carbon to a carbon, but that carbon's got a double bond. This is a carbon to another carbon without a double bond. And you're like, oh, there's also a hydrogen. And like, that's all just to figure out the bottom left one, which is, I think, one of the easier ones, the alcohol there. But like, yeah, so there's a shortcut to this of just like the only time we would ever include a dash or a wedge is if it's a chiral center. And there's 5 wedges and 3 dashes. So
let me ask you. Let's assume the AAMC wants to get mean, and they remove the dashes and wedges. Can you still get to the answer 8?
You could. It would be
just
very
takes you a
time
lot
consuming,
longer.
and I don't think they would ask that.
Okay.
Because they know that you have about a minute per question. Okay. And this is actually a good kind of like takeaway. A lot of times a student will get this question correct, but still in my mind, they kind of like missed something because they weren't looking at the dashes and wedges. So if you spend 5 minutes on this question, then you're going to miss some other questions just because you didn't get to them. So even if you get a question correct, it's really important to go back and see how long did I spend on it. And if you spent a long time, see if maybe there's a faster way. See if there's a shortcut. Look for like some sort of like backdoor to the question because they exist pretty often.
Yeah.
A lot of times the MCAT has 3 or 4 different ways to answer a question, kind of like the previous one where you're like, it's not going to be 200 or 400 because that's like insanely fast. That's like the speed of a bullet sort of thing. And so another question for the Blueprint course with the analytics is timing in that analytics as well. Yeah, keeping track of how long you're spending on each question. That's a really crucial thing that a lot of times students don't think about. They're just worried about, did I get the question wrong or not? But how much time you spent on the question is actually really crucial as well. We keep track of that.
Okay.
That also.
Sweet. So in my mind, what you're saying here is if a question is asking about chirality, if a question is asking about stereocenters, the potential initial first thought is dashes and wedges.
Yeah. And like I said, every question I've seen from the AAMC that is asked about stereocenters or chiral centers, they've left them in. I don't know why. It makes it so much easier if you can just like count the dashes and wedges. I'm not guaranteeing that it's always going to be the case, but everyone that I've seen so far has always done that. And that just makes life quite a bit easier.
Okay. All right. Question 17. It's all you.
All right. So the preferred ion configuration of many elements on the periodic table is determined by A, the electron configuration of the nearest noble gas. Elements will gain or lose electrons until they have the same core electron configuration as the noble gas. B, the electron negativity of the element directly above it. Within the same group, elements will gain or lose electrons until they have electronegativity that matches the period immediately above them. C, electron configuration of the nearest noble gas. Elements will gain or lose electrons until they have the same valence electron configuration as this noble gas. D, the relative stability of the nearest D subshell. Elements will gain or lose electrons until the outermost D subshell is stable.
So at its core, this seems like just like how is the periodic table arranged? Which I don't remember, although I did remember to count like 1, 2, 3, 4, 5, 6 over to the oxygen.
Yeah, it's also asking about this like preferred ion configuration. So ion is when something's like gained or lost, like calcium 2+ is an ion. Phosphate is a polyatomic ion, PO4 3-. We have to have some like plus or minus charge.
Let me see. So noble gas. So A and C both mention noble gases. B and D do not. So maybe noble gases is something related to it. The first part of A and C are both the same. Elements will gain or lose electrons until they have the same core electron configuration as the noble gas, or elements will gain or lose electrons until they have the same valence electron configuration as the noble gas. I don't know. Without knowing, right, without remembering, I'm like, well, A and C are very similar, so they're going to want to make sure that I understand the nuance between those two. So I'm going to stick with A and C as potential and hope that, again, I'm 50-50. And then I have to remember Will elements gain or lose electrons until they have the same core configuration or have the same valence electron configuration? And to me, I think it makes sense for valence electron configuration, not core electron configuration, because that would change what it is, wouldn't it?
Right. Like changing the electrons in the within the inner shells, like that's first off, that's way more difficult than like adding one onto the outside or taking one off of the outside.
Yeah.
And another way to kind of like think about this, like remember you can use outside knowledge. As a matter of fact, you kind of have to sometimes in the sciences. Just think of like, okay, what are some ions that I know of, like common ions? Like sodium chloride turns into Na plus and Cl minus. And so Cl minus, that starts to look like argon when it picks up an electron, and sodium, when it loses an electron, looks like neon. And so it's turning into kind of like the noble gas configuration, and that just makes sense. And it's absolutely the valence shell, because we pull or take them off of the outer shell, not the inner shells, because that's difficult and annoying. It's like trying to paint the inside of a baseball. It's a lot easier to add something to the outside of it. Rather than the inside.
Okay, so again, just without knowing anything, I just kind of said, what would a test writer want me to know? How are they thinking through this? Let me think through it in the same way.
Yeah.
Wow. Alrighty. So that is our first set of discretes here on full length 1 from Blueprint MCAT. Struggling. Wait,
first of several.
Do I have 528 still? I'm hoping.
Yeah.
All right.
Yeah, it's good to remember. You can miss a question or two and still get a perfect score on the MCAT. So we're gonna have to do real well on the rest of them for a 528. But